Hello everyone, I hope everybody's fine and healthy and ready to learn. We want to talk about the derivative of the sine function in the continuation of our lectures. The theoretical definition of a derivative is very clear for everybody. So we know that f prime of x or dy over dx in Leibniz notation is nothing but the limit of f at x plus h minus f at x all over h when h approaches 0. This is the definition, everybody knows that. Now in this case, we have f of x equals sine x. So we want to find the derivative of sine x. So I'm going to say f prime of x equals the limit of sine of x plus h minus sine of x over h when h approaches 0 by a simple substitution. Now I'm going to apply the compound angle identity or the addition formula for sine that we have learned in the past in studying trigonometry. That's a trig identity. So sine of x plus h would be sine x cos h plus cos x sine of h minus sine x, of course, all over h when h approaches 0. So now I'm going to rearrange the terms. So I'm going to take the first and last terms and factor out sine x, which is the common factor. So I get cos h minus 1 inside the brackets times sine x clearly. That is over x. And I'm going to at the same time break the limit down into two limits using the properties of limits that we remember. We used to say sum of limits equals limit of sum for two functions. And what is left over is cos x sine h over h when h approaches 0, clearly. So this is the sum of two limits. Now, we know that the main variable is h here because h is approaching 0. So sine x is not the variable. So we treat it just like a constant and we can write it outside of the limit. So we go sine x times limit of cos h minus 1 over h, okay, when h approaches 0, plus similarly cos x comes out just like a constant times the limit of sine h over h when h approaches 0, okay? Now this limit here, cosine of h minus 1 over h, is a limit that we have calculated in the past. So using our past knowledge, we know that this limit is equal to 0. And this other limit here, limit of sine h over h when h approaches 0, is also a very, very famous limit that I think we have proved it in the past. It is equal to 1. It's a very famous formula. Limit of sine h over h when h approaches 0 is always equal to 1. So if I add these two up, 0 times anything is 0, and 1 times cos x would clearly be cos x, solving the puzzle for us. So if somebody says, what is the derivative of sine function, sine x? The answer is right here. It's cos x. Derivative of sine is cosine. So I'm going to write this at some corner. I'm going to say y equals sine x. The derivative is cosine of x. This is something that is important. I have to remember that. Now, of course, you wonder, what is the derivative of cosine now? Obviously, right? So to find the derivative of cosine, I don't need to do this long method. There's a smarter way of doing it. So I'm going to say if f of x equals, let's say, cos x, okay, I can rewrite this cosine function, believe it or not, using this trig identity, which is sine of pi over 2 minus x. Because you know that sine of pi over 2 minus x is cos x, and likewise, cosine of pi over 2 minus x is equal to sine x. So instead of cos x, instead of finding the derivative of cos x, I'm going to be acting smart and finding the derivative of sine of pi over 2 minus x, okay? But the thing is that the derivative of sine of x, we know it's cos x. We just proved it 2 minutes ago. But this is not sine of exactly x. It's sine of some variable, sine of pi over 2 minus x, right? So I can use chain rule here. I can say, okay, this is like some variable, like, I don't know, let's call it like theta. So theta is equal to pi over 2 minus x, okay? And we can find the derivative, which is f prime of x, using the chain rule. We can say this is basically sine of theta, and we can say that the derivative of y with respect to x is in fact derivative of y with respect to theta times d theta over dx. This is clearly chain rule in Leibniz notation, which we have studied in the past. So what is dy over d theta? That's derivative of sine theta with respect to theta. Well, the answer is right there. It's cos theta. We just proved it 2 minutes ago, didn't we? So that is cos theta right there. But then times d theta over dx is the derivative of theta with respect to x. So here, if I find d theta over dx, derivative of theta with respect to x would be derivative of pi over 2 minus x with respect to x. But pi over 2 is a constant whose derivative is 0. Therefore, the answer would be just -1. So I just multiplied by -1, and I end up with negative cosine of theta. But what was theta? Theta was pi over 2 minus x, right? And we said that cosine of pi over 2 minus x is the same as sine of x. But there's a minus sign in front, so it becomes negative sine of x. Making long story short, if f of x is cos x, the derivative of cosine function is equal to negative sine of x. And this is something noteworthy of writing it at some corner. I go y equals cos x. The derivative is negative sine x. I gotta remember these important formulas that we are proving one after another. So sine, cos, and obviously comes tangent, right? So we want to find out what is the derivative of tangent. So y equals tan of x. I want to know the derivative. But the thing is that instead of using all these other techniques, why don't I use trig identities? Why don't I say tan x is actually sine x over cos x? Is it not true? And then what you have in front of you is nothing but a simple quotient. So I'm going to apply quotient rule. I know what you think. You say this is a smart way of doing it. I agree with you. I'm going to apply quotient rule. So I'm going to say y prime equals derivative of top, which is cos x, times bottom, which is another cos x, minus derivative of bottom, which is negative sine x, times top, which is just sine x, divided by the denominator squared, right? So I get y prime equals cos squared of x plus sine squared of x divided by cos squared of x. I don't need to remind you of the famous Pythagorean trig identity. Sine squared of x plus cos squared of x is equal to 1. So I'm going to write 1 over cos squared of x. But you know that 1 over cosine is actually secant of x, because secant is the reciprocal of cosine function, isn't it? So instead of saying 1 over cos squared, why don't I just say secant squared of x? And French say voila. There you go. We found the derivative of tangent x. So I'm going to add it to my list. Y equals tangent of x. The derivative is secant squared of x. And these are the formulas that in the next, I would say 2-3 years, you have to know them very well. You'll be using this a lot in university. For now, I just prove these 3 formulas, and then we're going to prove more formulas in the next lectures. Okay, thank you very much.